Greetings, 2%ers. We're going to do another Diagnosis and Understanding series for the playlist. The Diagnosis and Understanding series comprehensively covers automotive concepts and component function and things like that. And today we're going to talk about one that many of you guys may not be very familiar with, probably heard of. We're going to talk about voltage drop and why, as an advanced do-it-yourselfer, it's going to be critical for you to know what voltage drop is, how to test for it, and most importantly, of course, how to understand voltage drop so that you don't have to rely on flow charts or instructions. You'll be able to come up with your own voltage drop tests because after this video, you'll master the concept of voltage drop. So let's start off with why, especially for many of you guys who have been doing your own auto repair and you're very good at it, you know how to replace things without help, you are well familiar with how to use your DVOM and do electrical testing, and you've gotten by all this time without ever having to do a voltage drop test. Well, let's go ahead and put that to the test. Let's do the simplest diagnosis that there possibly is on a car. Let's look at a no cranking, no start and see how our scientific diagnostic testing thinking ability holds up if our skills do not include voltage drop knowledge. So here I have a very, very basic starter setup here with an ignition switch that I made. So this would of course be in the car, we would say. And we turn the key or hit the ignition switch and nothing happens at all. Now, of course, for your 98%er, this is about the easiest diagnosis you can do. You replace the battery, and then when that doesn't fix it, battery works, car don't start, you need a starter. But I actually got the idea for this video from, I was at an auto parts store, and as I was in line to buy my parts, a guy had bought a battery and a starter. And then later in the day, when I was returning the core from what I replaced, the same guy was actually there at the store trying to return his battery and starter because his car still didn't start. Now, of course, that would never happen with us because we are advanced diagnosticians. And because we are more advanced do-it-yourselfers, and we actually are one of the 2% of people that would spend time on learning about a starter system, the components, and how to diagnose exactly what might be wrong, we would come up, of course, with a list of all the possible variables that could explain this situation other than the battery and starter. As you see, there are quite a few of them, and most of you guys are certainly familiar with these. So let's go ahead and use our logical reasoning scientific approach and go ahead and rule these out and see where our no start problem is. And then let's see where we go wrong with this, because this looks like it's going to be pretty comprehensive. So if your first instinct is not to test the battery, then you are on the wrong channel. But obviously in a car, this would be the easiest thing we would do. All of you guys should know, of course, how to test a battery. So let's go ahead and check. We've got a little bit low on the battery, but of course that might be expected with a starting problem. So we've got our 12 volts at the battery there. And of course, most of you guys are well aware that just because we have 12 volts at the battery, that does not mean the battery is good. When the battery is put under load, we could very well expect the drain on the battery. So we are going to go ahead and test for that with the starter. So let's turn the starter on. And we see we drop voltage down a little bit, so there is definitely some activity there, but it's not very much, not as much as we would expect. Maybe that's a clue. But whatever the case is, we also could do some other things. We could turn the headlights on. We could take it to a auto parts store, have it load tested. But whatever case, whatever we do, we are going to rule out the battery as the problem here. Okay, so battery is ruled out. The next thing we're going to see, obviously we know any problems with loose connections or dirty terminals or things could cause that. So let's take a look. And of course, this would mean going through, doing all the basic stuff of cleaning the terminals, making sure everything's clean and tight. Some people might even be inclined to maybe go ahead and verify that we've got good continuity here with our terminals. We've got no resistance there. We might check other places and see that we've got continuity. So we have eliminated terminals and bad connections. All right, the next thing, of course, it could be that we have some type of ignition switch problem. So various ways we could check an ignition switch. One way I like to do it is to just jump the solenoid and bypass the ignition. If we get the starter to turn over then we know that there was some control issue, ignition issue. We could also, of course, do a continuity test and then turn the ignition key, and we see that we get continuity then, but turn the key off and we don't. We could check for voltage there, in fact, so all of you guys know that stuff. But we could do all kinds of tests to verify and rule out that there is ignition control problem. And by grounding out the solenoid, we get a little bit of a spark there, but we can see the starter does not move. This rules out just the fact that we can do this. This rules out pretty much that we have any kind of ignition problem. I guess we could have an ignition problem and this issue, but the fact that we're seeing some electricity there, this, along with our other ignition tests, we've ruled out ignition. All right, so at this point, it is definitely looking like it's going to be the starter, because if you saw the sparks there and everything, it does indicate some electrical. But remember, we need to be absolutely certain when we put a starter in, because maybe you guys have the same policy that I do when I do work for people. If I am wrong about the starter, I buy the new starter. I have to pay for my mistake, so I want to be absolutely sure. Relays would be next. We have a video on the Diagnosis and Understanding series of how to test relays. So you can watch that video and then ruling out if a relay issue. Another thing could cause this too. Remember, this system that we've got set up would be in the car. Maybe the engine won't turn over. Maybe the engine has a spun bearing. Maybe there's some type of accessory issue where the accessories are binding the serpentine belt. Not likely here. We don't even hear the solenoid click. Really indicative that we've got a bad starter. But even so, you might be inclined to go ahead, get a ratchet, turn the engine over by hand. We can verify that there is no mechanical interference issue. We are down now to wiring or the starter. So, being fairly confident that this is a complete waste of time, we're going to go ahead and look for voltage at the starter. And of course, this, for many of you, would have been the second or third thing in a row, but I'm kind of doing this on purpose. Let's go ahead and check our wiring now. And we can go to a ground here. And here, let's go ahead and keep the leads in order here just for simplicity. The yellow wire here is a ground, of course. I made it yellow so that it would stand out against the dark backdrop here. Let's go ahead and check ground, and let's go ahead and check voltage, and check that out. We have battery voltage at the starter, so we know that our wiring is good. Maybe we weren't so convinced of that, so let's make another mistake. Let's go ahead and check for continuity. We know there's continuity there, but let's go ahead and check for resistance. So we go ahead just to be safe, and granted the cable's a little bit old here, but let's test for resistance, and we see that we have just a couple tenths of an ohm of resistance. Not anything to be concerned about. Pretty much, actually, it's almost a tenth. So virtually no resistance at all. We're not very worried about that. Even a new cable might have that. Let's go ahead and also, just to be safe, go ahead and check our continuity and resistance on the ground wire. And we can see on the ground wire we have just about the same. So no resistance issues. We have pretty much ruled this thing out, it looks like, haven't we? Let's go ahead and look at the starter. So through our systematic approach, we have deduced that the only possibility left is the starter. We are very confident on that, but just to be absolutely sure, before we go ahead and replace the starter, let's go ahead and pull the starter out of the car, bench test it, verify that the starter doesn't operate. So after calling the parts store and verifying they have a starter in stock, let's just make sure the starter doesn't run. And uh-oh. Well, we've got a problem here. The starter does... Actually, that's not really a problem. So we, of course, conclude that the starter, of course, has to be bad. It's the only possibility. But there's a massive difference between just free spinning the starter outside of the engine with 12 volts to it like we just did versus having the starter have the extra load of actually turning over the engine. So the starter must be bad. It's just when it's under the load of turning over the engine, it can't work. But when it's free spinning outside of the engine, of course, it turns. But if there was any load on it, it wouldn't. So we conclude that despite that bench test, the starter has to be bad. Just to be safe, let's go ahead and verify it's not an issue with any kind of resistance or anything. And that little tiny bit of resistance in the battery cables isn't an issue. So let's measure the resistance on our jumper cables that we use that we know work. So just to be scientific about it, we go ahead and see if we've got any resistance here. And look at that. We actually, by that reading, have more resistance in the jumper cables that worked than in the battery cables, verifying without question the only possibility we have a bad starter, and we go ahead and buy a starter and put it in the vehicle. All right, new starter in the car. Maybe if this is a customer, you've already called them while you were installing it to give them a head start to get over and pick up their car early. And we go ahead and hit the ignition switch. And no way. No way. Let's double check our connections. Everything's good. Wow. That's the problem. Where did we go wrong? So how is it possible that using our scientific, methodical approach, we ended up no better than 98% of the people that would have just guessed a starter from the beginning, and we both ended up putting a starter in the car when it didn't need it? Our mistake was in ruling out the wiring. We actually did not properly rule out the wiring because we did not consider for voltage drop. And actually, that is where the problem is. The problem is with bad wiring in this starter motor. There is high resistance in the positive battery cable, but there can't be. We measured 12 volts at the starter, so there can't be bad resistance there. Furthermore, we even did a continuity test and measured no ohms on the wire, actually less, if anything, than there was on the jumper cables that worked. So how is it possible there could be high resistance in the wire? It's because we don't understand the concept of voltage drop, but that is indeed what the problem is. And in order to really understand it, I could show you how to do a voltage drop test in 2 minutes, but what we're going to do is understand the mechanism of voltage drop so that you will understand the concept. You won't have to look up how to do a voltage drop test for the rest of your life. You will know how to do it, and you'll also be able to come up with your own testing methods. So let's go ahead and look at what voltage drop is, and then let's look back at our wiring tests, and then it'll be very apparent where we went wrong. And before we do that, just to verify this is indeed a wiring problem, I'm going to remove that bad battery cable. We're going to install this good battery cable, and we can see that the starter works. So obviously the bad battery cable was the issue. And just to show you, our resistance measurement with the ohm meter shows the same as the cable that didn't work. All right, conclusive proof. We somehow made a mistake on our diagnosis that the wiring was not an issue when it absolutely was. So, as you guys probably know if you follow the channel, electricity is by far my weakest attribute. And for many of you, I know it is too. And for many of you, it is not. I know I have several electrical engineers on the channel. We are not going to go into things like Ohm's law and stuff like that, but the way that I get by electrical issues and understanding electrical problems and coming up with ways to test them is by sort of using an analogy with water. That's kind of how I do it, and that's what I'm going to show you. It's not exactly a physically accurate analogy to electricity, but it will get you by for pretty much 99.9% of anything you're going to run into in automotive electrical, including what we ran into here. So let's go ahead and draw up a very simple circuit here. All right, so let's start with a very oversimplified diagram of our starter circuit, ignoring the solenoid. And by the way, some vehicles even have firewall-mounted solenoids that you would also need to check in a diagnosis. But obviously, it seemed very obvious that our problem was with the starter. We verified good ground. We measured 12 volts at the starter between the power and ground. We measured continuity and no resistance with the cables. Obviously, you all well know the ground actually goes back to the battery. And actually, just for simplicity, we're going to go with kind of a conventional electrical theory here, because as most of you do know, electrons actually do leave from the negative terminal on a battery, but we're going to go with the positive flow just because I want you to master the voltage drop concept here. Again, this is not an engineering class, so we're going to go with this system that most of you are more familiar with. And then my way, when I think of electrical, I actually think of it in terms of water and pressure, particularly with voltage. So if we look at a similar setup here with water, we would have, of course, water flowing through this hose here. And of course, the water does some type of work. Maybe there's a sprinkler at the end of the hose. I tried to draw a water wheel here, but pretty much a similar thing as what we would have here, where you've got a flow of electrons through the wire and it does work at the starter. Now, the mistake that we made was when we looked at continuity of this system, you have to have the system under load. There has to be flow through here. Why? Well, again, it's easier to think of it in terms of water. So at our battery, we of course have 12 volts. And we can think of this as water pressure. So just like at our water tap here, with our water flowing through the hose, we have, say, 12 volts of pressure here. Now, anywhere along this hose, we should have 12 volts of pressure anywhere along it until it actually gets to doing the work. And that would be the same thing here as well. We should be measuring 12 volts anywhere. If we were to do a voltmeter between the negative and anywhere along this positive wire, we should have 12 volts up to the starter at any given time while the starter is working. If we do not have the same voltage as battery voltage, that is known as voltage drop. Now, what is the cause of voltage drop? Well, let's look at our hose example. Let's say that we put a kink in this hose. And we kind of step on the hose or pinch the hose. So the kink is going to restrict the flow. And you can kind of think of it, if you put your thumb over the end of a garden hose, if you let your thumb off a little bit, of course, the water sprays out, but you have much more pressure at your thumb than you do after your thumb, obviously. So think of it as a kink in the hose. The same thing can happen in an electrical circuit. And in an electrical circuit, we would have some type of, not so much a kink in the line, but some type of resistance, corrosion, something like that, where we would have a drop in the voltage after the resistance or the restriction. And of course, that drop in voltage may not be enough to do the work to activate the starter. And that is, in fact, what happened in our starter example here. So here's the thing about this, is that this only applies when there is flow through this hose. Let's do this, for example. Let's go ahead and cap off the end of that hose. So the end of the hose is closed off. Do you see now, I hope, that the water is going to go through the resistance, but build up the same pressure on both sides of the blockage because we've capped off the end of the hose. And that was our first mistake we made when we measured the voltage on the battery terminal. What was the first thing we did? We did not have the starter operational. We have some type of resistance here, but we measured 12 volts at the starter. Why? Because it's capped off. There is no flow because we were not operating the starter at the time. To see the effects of a restriction along a system, you must have flow through it, just like with water. And that was our first mistake. Now, there was a second mistake that we made, and it seems to be like we didn't make a mistake. We measured for resistance in this wire using the ohm meter, and we found no resistance. We actually found less resistance than in a known open hose or wire. So how come that happened? Well, that actually is more with understanding how your volt-ohm meter works. But basically what happened in that situation, so the reason that our ohm meter test did not show resistance on a wire that clearly has a ton of resistance is because that wire, that battery cable is kind of more like a drainage pipe than a garden hose. So if we can think of an obstruction in this drainage pipe, and the way that your volt-ohm meter works is it's kind of like, again, using the water analogy, instead of flooding water through here and looking, if we had a massive amount of water through here, then obviously we would see that drop because of the restriction at the end of it, but that's not the way that your DVOM does it. The way your DVOM does it is it's almost like taking this drainage pipe with the blockage and then just pouring out maybe like a half a cup of water into it and then just checking to see that we get water coming out on the other side. Well, obviously with a very low trickle of water, that's going to have no problem making it through, and we easily detect it on the other side. So again, we're not really loading the circuit. We're just sending a trickle through there. And if there's any kind of integrity through that corrosion, there will be full continuity measured. And that is why our continuity test failed us. So our first mistake, obviously, we now understand we were measuring a capped off system initially, because without running any current through the starter, we basically took our DVOM here, we measured from negative to positive at the starter, and of course we measured 12 volts. But we understand now that even after a restriction, without flow in the system, because this is capped off, there's no flow, we measured the 12 volts the same way we would have measured it with a kink in the hose. So now we know that we need to have flow through the system. But the other thing that we need to do is we have to understand that the way a DVOM works is by measuring difference in potential. So what we need to do is activate the starter, cause the actual flow to occur, which creates that voltage drop, but move our lead to battery positive so that we can measure that potential difference between the start of the flow and after any obstruction. When we do this, we would see 3 volts on that meter, representing the amount of voltage lost because of the resistance or corrosion in the wiring. Notice, by the way, that you always have to have everything add up to your source voltage. So just to test our knowledge, if we were to measure here and here, just before the resistance, what would our meter measure? Well, it would of course show 0. There should be no voltage drop in the good system, so there's no change in potential. So we should measure 0 there. If we were to measure here and here, then of course we would see the difference in potential. We would see that voltage drop. So there's various places where we could measure. If we wanted, we could even do this. We could measure from the battery, and then we could take this lead and move it to various points along this cable until we found the voltage drop. That, if we were interested, would allow us to find a bad region in the cable, if there was one. Oftentimes the cable is completely corroded. And as a matter of fact, sometimes on cables you will read ohms on the actual cable itself, but not always, as we just saw in this example here. So there's various ways, and I'll even show you another way. But now that we understand this concept, let's go ahead and repeat our tests on the wiring and see if we can catch that voltage drop. All right, so let's go ahead and set up again and repeat our initial mistake. So we, of course, if we measure negative to positive, we see we've got our 12 volts there. But what should it be now if we try a voltage drop test? And we know that this cable is bad, of course. What should our voltage be when we set over to the positive terminal? And it should read pretty much 0 because the system is capped off. So even wherever the resistance is, whether there's one point of resistance or the whole wire has resistance, because there is no flow through the system, it's like a closed off garden hose. Any point we measure, there's going to be the same 12 volts, so we do not have a difference in potential along the wire. Now, when we go ahead and apply actual current flow by hitting the switch, let's go ahead and see what happens. And we can see that we read about 9.4 volts, a tremendous amount of voltage drop. So we have a significant loss of voltage because of resistance in the wire. Because everything's going to have to add up to the battery source voltage, we know that the reason this starter is not working is because it's only getting approximately 3 volts. And another indication is, as I leave this on, the wire gets quite hot. So it's a little bit different than our obstruction example. One of the reasons for the resistance is because of generation of heat, which of course does not apply to a water analogy. Now that we understand the concept of voltage drop, let's see if we can use a more methodological approach and come up with an easier way to test this system. And there's a few ways to do it. But one way, would it not be easier, rather than running our leads through the car, around the engine, making sure we were clear of the serpentine belt and all that, just in case the vehicle started? Let's think about this. If we apply current through this system, then that would mean that we would actually have only 3 volts coming to the starter because we have 12 volts originally, 9 volts lost through the voltage drop. So if we were to measure from here to the ground, which might be easier to do because that way we just stay under the car and not have to run our wiring everywhere. And of course, we see our battery voltage here, but when we actually apply the current this time and measure that after the voltage drop, we should see about 3 volts. And you can see we see about 2.2 volts or so. As you can see, this is another way that we could measure the voltage drop. By putting the current here and measuring that voltage, we can now move our terminals up to the battery, and we can see our voltage at the battery there. In a good running system, we would have 12 volts pretty much from the source to the ground, even with the current flowing, because again, a good system will have very, very, very minimal voltage drop. So let's go ahead and verify that by going ahead and putting in the good battery cable and verifying that we do not have voltage drop. All right, so now I know I've got a known good cable installed here, which actually, if anything, may have measured more resistance with our ohm meter than the bad cable did, but of course we understand that that resistance measurement is completely useless on a battery cable. So let's go ahead and repeat our test. So let's go ahead and put our lead onto the battery positive here. And we know that when we put our lead onto the battery positive down here, we will see no difference in potential because it is a closed system. It is capped off. So regardless of any resistance, the pressures would be equal at any point. But now when we go ahead and we add flow, let's see if we read 9 volts. I don't think so. And we can see our voltage drop is approximately 1/10 of a volt. Very reasonable. Generally with voltage drops, I look for, if it's more than 0.5 volt, I get a little, fairly concerned. Anything under a couple tenths of a volt, I don't even blink an eye at. So we can see we have just very minimal voltage loss. Oops. And that's why the starter is able to run, because we are getting 12 volts through the motor. So let's go ahead and do this. Let's do our other way, because we know that we should not have any loss of voltage through the wiring. If we measure at this location with current flow, we should have about the same amount of voltage drop. So let's go ahead and see. And you can see that we've got about 10.5 volts. Let's go ahead and compare that with our source voltage. And we see that we've only got a couple tenths of voltage drop. Our battery is getting very weak, by the way, from all of this playing around. But a total difference now that we've got good continuity with no resistance through the wiring. And another thing that we know is that if we go ahead and bypass the switch and we ground the solenoid, we would be able to start the engine by grounding the solenoid out, because we no longer have the lack of voltage delivered to the starter. And yet another way that you could do this test, and this is something that I'll often do in the field as well, is not necessarily to even do the voltage drop measurement, but as a way to rule out that you may have a bad cable or something. Of course, electricity always takes the path of least resistance. So by going ahead and hooking up here and using a jumper cable or something to bypass the suspected bad wiring, now if I have the person start the engine, we can see it runs. But without the good wiring in place, we do not get the starter to start. So this is validation that, of course, that cable I bypassed must be bad. All right, well, hopefully that was helpful and gave you some more tools in your toolbox of knowledge, and also some new ways of using your DVOM that you maybe didn't consider. But it is definitely hard to remember to consider voltage drop. We're so used to checking for 12 volts at an accessory or 12 volts at a bulb or system, and we see 12 volts there, so we assume that the component must be bad. As you can see, unless you are actually considering flow of electrons through that system, that would be a false conclusion. Now, there are some times when I always consider voltage drop as a first thing that I'll consider. Any kind of headlights or taillights or any kind of lighting systems that are dim, you can see where voltage drop in the wiring would explain that. Typically, you would unplug the suspect bulb. You would look for 12 volts at the system. There's 12 volts, has to be a bad bulb. As you can see, wiring with even a little bit of voltage drop could cause that bulb to run dimmer. So you'll want to actually do a voltage drop test there to consider. If this starter were chattering as opposed to a complete no start like that, that would also be indication, possibly some voltage drop. One time I always do voltage drop is the diagnosis on a fuel pump. If there is voltage drop on the wiring to a fuel pump or bad ground or something like that, that will cause the pump motor to operate slower. That could be the cause of the lean condition that I diagnosed as a bad fuel pump or through fuel pressure. But before changing the fuel pump, I'll always do a voltage drop to test that. And further, what I'll do is I'll directly apply 12 volts directly to the fuel pump, see if the pressure increases, and if the pressure remains the same, then I can absolutely diagnose a fuel pump. As a matter of fact, the second video I ever did, I did exactly that, but the voltage drop testing didn't show up so well. It was before I got HD and all that. But those are 3 times when I'll just actually do the voltage drop test maybe first before I even do a regular voltage test. So just keep that little trick in mind. Hopefully you found this helpful. Thanks for watching.